Okay, so today we're going to talk about the beginning of chapter 16. So this will be lecture number 13. We're going to be going over, in chapter 16, acids and bases. So acids and bases, we have talked about them in the past, but we're going to go into much more detail about acids and bases in this chapter. Okay, so first, just as a reminder, acid is a substance that neutralizes the base. And that turns litmus paper red. It's generally going to have it's going to have a pH less than 7. Okay. Bases neutralize acids. And they turn litmus paper blue. And these are going to have pHs greater than 7. Okay. So one of the main things we're going to be looking at in this chapter, we're going to be looking at equilibrium in terms of acids and bases. So we talked about the idea of strong electrolytes and weak electrolytes back in 1211, and we brought it back up in the beginning of 1212, and we can look at acids and bases in terms of weak or strong electrolytes. If we have a strong or weak acid, strong acid or base, this is going to have no equilibrium process. So this will just be a one-way reaction when we put it in water. So if we have some generic acid, we put it in water, it's going to dissociate completely into H+, which will then attach to a water molecule and produce hydronium. We'll bring up the idea of hydronium many times, but hydronium is just water plus a proton, and then a minus our anion. With a base, we have some BOH. We add it to water. It doesn't actually do anything with the water. It just produces B+ ions, OH- ions, and then the water still just kind of hangs out. So the water doesn't really interact with the base at all. Now, with a weak acid or weak base, we get an equilibrium in water. So we have the same idea, this HA plus water. We now have our equilibrium arrow, and we still have the same products. This is just based on the strength of this acid. Okay. Same thing if we have a weak base. So we'll have no H, or no OH in this case. So actually usually we'll look something like this, and in water, we'll get that. And it's still an equilibrium process, so this is a weak base. And we'll produce a cation and hydroxide ions. In both the case of the acid and the base, we'll have this very similar products, whether it's weak or strong. There's just slight differences, especially with the equilibrium. Okay. We can define our acids in a couple different ways. So, or acids and bases. We have an Arrhenius acid. Same guy who brought us the Arrhenius equation. And we have an Arrhenius base. An Arrhenius acid gives off H+ ions in water. An Arrhenius base gives off hydroxide ions in water. We have a Bronsted-Lowry. Acid. This is a substance that donates a proton. A Bronsted-Lowry base. Accepts a proton. And then we have Lewis acid, Lewis base. Same as our Lewis dot structure guy. Lewis acid accepts a pair of electrons. And then a Lewis acid, or sorry, Lewis base donates a pair of electrons. So we'll look more in detail about those definitions and limitations in class, but just know that we can define acids and bases in terms of either Arrhenius, Bronsted-Lowry, or Lewis. Okay. So, like I said, we'll go much more in detail about all three of those types, but now let's look at what's called a conjugate acid-base pair. So this is when we have a species that differs only by the presence or absence of a proton. We call it a conjugate acid-base pair. Remember, a proton, that's H+. It's a conjugate acid-base pair. Okay, so for instance, if we have HA plus B goes to BH plus A minus. If we look at these two species, they differ only by this proton. So this would be a conjugate acid-base pair. And then This one and this one differ only by the presence or an absence of that proton. This will be a conjugate acid-base pair again. Okay. We'll do some examples in class to go more in detail on that subject. Okay, let's look at our acids and bases within water, or let's look at the acid-base properties of water. So water has a pH, pure water has a pH of 7. So it is neither acidic nor basic. Unless placed in with acid or base. If you place water in with an acid, it'll act as a base. If you place water in base, it'll act as an acid. If we just have pure water will actually react with itself. So if we have 2 water molecules, for instance, they will react with each other, where one substance, just going to highlight this hydrogen right here, one substance will take a hydrogen from another, one water molecule will take a hydrogen from another water molecule, and you will produce hydronium. Right there with a plus, and then you will also produce hydroxide with a minus. So these would be conjugate acid-base pairs. These would be conjugate acid-base pairs. Okay. Oh, sorry. These would be conjugate acid-base pairs. These would be conjugate acid-base pairs. So we would say in this case, since this is donated proton, we would call this the acid. This would be the conjugate base. This would be the base because it is accepting a proton. This would be the conjugate acid. Okay, so we have our conjugate acid-base pairs. Acid on the left side, base on the other, base on the left side, acid on the other. So that's how an conjugate acid-base pair works. It'll be acidic on one side, basic on the other. So with water reacting with itself, we call this the autoionization of water. And this process is not overly favored. We'd actually, if we were looking at our equilibrium expression, so our KEQ for this would be 1.0 times 10 to the negative 14. So it is mostly in the water form, not very far into the hydroxide hydrogen content. So we actually call this KW for water. So the KEQ for water is KW, and that is equal to our hydronium concentration times by our hydroxide concentration. The left side is nothing but water. Our reactants are water, so they would not be included in this. So our KW is 1.0 times 10 to the negative 14. So that means in pure water, we would have H3O plus concentration equaling OH minus concentration, and they would both equal 1.0 times 10 to the negative 7. Okay. So So one of the other things we're going to be looking at in this lecture is pH and pOH. pH measures the H plus concentration, or it's a measure of the H plus concentration. pOH is a measure of the OH minus concentration. Okay. To determine pH, we have pH is equal to negative log H3O plus concentration, or pH is equal to negative log H plus concentration. This is in water, which is what we'll always be doing, and this is not in water. And then we can also figure out pOH. It'd be negative log OH minus concentration, and that's the only option we have. And these are on a logarithmic scale. So if you have a H plus concentration equal to 1 times 10 to the negative 1. You have a pH equal to 1. If it goes 1 times 10 to the negative 2, you have a pH equal to 2, and so on and so forth. Same thing with your OH minus. So as we change by a magnitude of 10, we change our pH by a unit of 1. So our pOH, if it's 1 times 10 to the negative 1, we have a pOH equal to 1. Okay? So we will look at examples of how to do pH, but some things to note. We could use that whole KW equal 1.0 times 10 to the negative 14 to equal our H3O plus times by our OH minus concentration. So if we know one of these concentrations, we can determine the other one. So just looking at some equations we're going to be using. And then if we have our pH plus our pOH, if we put those together, will actually equal 14.00. So if we know our pH or our pOH, we can determine the other one. In class, we'll go over some examples, but this is everything for the pre-lecture review.